Okay, this is a review for our Unit 7 test, which will be tomorrow. So I'm going to go through our Unit 7 notes and ask questions that can be answered by the notes as a way to study and help you prepare for your test. Okay, so we know from previous units that force and motion are related to each other. And we have talked about this in our force unit, gravity unit, and in subsequent units as well. In this unit we really focus on this when we talk about Isaac Newton's laws and how he addressed this relationship between force and motion. So, for example, we could say when a golfer hits a golf ball perfectly with their driver, what happens? And we can ask the question, if you make a perfect shot, a perfect golf shot, you hit the golf ball with your club, does the ball just sit there on the tee? And of course, the answer is no. If you're hitting a perfect shot, it's flying off down the fairway. All right. So, first question we could ask, there's two questions I could ask here with our next line of notes. First, who explained the relationship between force and the motion of objects and came up with these three laws of motion? And the answer is Isaac Newton. And the next potential question, which is a little more trivial in nature, is what year did Isaac Newton formulate his laws of motion? And the answer is 1686. So in 1686, Sir Isaac Newton explained the relationship between force and motion of objects with his three laws of motion. So next we could say Newton's first law of motion describes the motion of objects that have what kind of net force? And the answer is objects that have a net force of 0 newtons. In other words, objects that have balanced forces. So we're talking about objects that are either sitting still or they're moving in a constant way with a constant velocity. So they're moving with speed not changing nor direction changing. So which law states that an object at rest remains at rest and an object in motion remains in motion in a straight line and at a constant speed unless acted on by an unbalanced force? And the answer is Newton's first law of motion. So another example, like the golf ball example, if you throw a football, if there are no other forces such as gravity or friction acting on the football, what will happen if you throw a football? And the answer is the football will fly off in a straight line forever at a constant velocity. Now when we look at Newton's first law of motion, it's important to understand, or it's a little easier to understand this law if we look at it in its two different parts, because it talks about two different situations. So the first situation that Newton's first law of motion talks about, or what is the first type of situation that Newton's first law of motion describes? And the answer is it describes how the motion of objects that are not moving, or it describes the motion of objects that are not moving. Now, what's another term for objects that are not moving? Well, in physics, we may say that objects that are not moving are at rest. So another example, back to the golf ball example, which is also shown down here at the bottom of the page. The golf ball sitting on a tee, not moving, is at rest. The golf ball balanced on the tee is at rest. It has a net force of 0 newtons, has no velocity at all. Its velocity is not changing, so it has no velocity, no acceleration, and it has balanced forces acting on it, net force of 0 newtons. So, and a question could be asked, how long will that object that's at rest stay at rest? And the answer is the object at rest will not start moving ever until there is some unbalanced force applied to that object. In other words, some push or pull. The golf ball will sit on that tee forever until something pushes or pulls it and creates an unbalanced force situation. So objects at rest will not start moving until some push or pull is exerted on them that creates an unbalanced force situation. So in the case of the golf ball, the unbalanced force is coming from the golf club that hits the golf ball, and that is a form of a push, and then causes the golf ball to fly off the tee, down the fairway, or into the rough, depending on how your shot goes, or the woods, or the water. Okay, the second part of Newton's first law of motion deals with what kind of object. And in this case, we're talking about objects that are moving. So when we are looking at objects that are moving, we can say what will cause an object, how will an object that is moving move? And the answer to this question is an object that is moving will not change its speed or its direction unless there is some push or a pull exerted on the object. So unless there is some force exerted on the object, it will continue to move in a straight line at a constant speed. So, for example, and this is a dramatic example here, of course, but this is maybe a little easier to understand. If you have a car that's driving at a constant velocity, that means that it is moving at a constant speed and in a straight line in one particular direction. Let's say it will keep moving at that constant speed and constant direction until an unbalanced force acts upon the car, and in this case, the example I have here is that there's a tree, unfortunately. So a car moving at a constant velocity will keep moving until an unbalanced force in the form of a tree changes its motion. So this is a rather abrupt end to the motion of this car. Now what about the passenger in this car? If there's a passenger in the car, what will the passenger's body do in this situation? Well, when the car is driving at a constant speed in a straight line without changing direction, the passenger in the car is doing exactly the same thing. The passenger in the car is moving at a constant speed in a straight line, the same as the car. However, when the unbalanced force of the tree changes the motion of the car and causes it to slow down, the person in the car is not experiencing this unbalanced force coming from the tree directly, so their body will continue to move in the straight line at the same speed as before the car hit the tree. So this is what makes car accidents dangerous. So hopefully the unbalanced force that stops the passenger from moving forward in a straight line at a constant velocity or constant speed will be something like a seatbelt or an airbag and not the windshield. But these are this is a situation that arises when you have an unfortunate car accident like this. So, next question. Why is observing the effects of Newton's first law often difficult? And the answer is because of friction. Because friction, we always have friction involved with basic movements going on that we observe all the time. And friction makes the observation of this law a little bit difficult in its purest form. So, for example, what does friction with air do to a thrown football? And the answer is friction with air causes a thrown football to slow down. What does friction with the road between a car and the road on a level surface cause the car to do if someone lets go of the gas? So you're driving on a car on a flat level road and you let go of the gas. What happens to the car? And there's friction with the road, and there's friction within the wheels and the engine as well. Well, the answer is this causes the car to slow down as well. So these objects that are moving are not continuing on at the same speed or in the same direction forever, as Newton's first law seems to say that they will, but that's because there's this hidden effect of friction, this hidden force of friction creating an unbalanced force situation that it's not necessarily easy for us to observe directly, but it's still there. So is there ever a situation when we encounter moving objects in our everyday lives where there is no friction? And the answer is no. In our everyday lives, friction is always present in our everyday lives whenever we encounter moving objects. This little item here at the bottom will show up on the next page. Okay, next question. What is another name for Newton's first law? The answer is Newton's first law is often called the law of inertia. So next question, what is the tendency of an object to resist any change in its motion, whether it is starting, stopping, or changing direction? And the answer is inertia. Inertia is the tendency of an object to resist any change in its motion, whether it is starting, stopping, or changing direction. Next question, what objects don't have inertia? The answer is none. No objects don't have inertia. In fact, all objects have inertia. And there's the bell. All objects have inertia. Next question, what causes you to slide against the door of the car? If you're a passenger in a car and the car makes a sharp left turn, what causes you to slide up against the door? And the answer is, again, inertia. Inertia causes you to slide up against the door when your car makes a sharp turn, because there's forces acting on the car, unbalanced forces acting on the car, causing it to change direction. But your body, just like the car hitting the tree, your body wants to continue moving in a straight line. So when the car turns, you want to keep going, and so that causes you to slide up against the door, and then the force of friction with the seat, your seat belt, and force applied from the car door all stop you from flying off in a straight direction, straight off the side of the road. Okay, next question related to this topic. What is mass actually a measure of? And the answer is mass is actually a measure of inertia. Inertia and mass are essentially the same thing. The more matter inside of an object, the more inertia it has. So if an object's mass gets larger, then what happens to its inertia? Well, the larger an object's mass is, the greater its inertia will be. Next question. If an object's mass gets smaller, what happens to its inertia? And logically, the smaller an object's mass gets, the less its inertia will be. So, our next question here is it easier to change the motion of an object with a small mass as opposed to an object with a large mass? And because inertia is the tendency of an object to resist any change in its motion, the answer is, and because smaller objects or smaller massed objects have less inertia than larger massed objects, the answer to the question, is it easier to change the motion of an object with a small mass than an object with a large mass? The answer is yes. It is easier to change the motion of an object with a small mass than that of an object with a large mass, because the object with a large mass has more inertia. And there's a good example that is shown here on the right. If you are pushing a bicycle and pushing a car, it is much more difficult to push a car than to push a bicycle. However, once you get the car moving, it's really difficult at first, but once it gets moving, it then becomes more difficult to actually stop the car from moving, because that's a change to its motion, than the bicycle. So you get the bicycle moving more easily than getting the car moving, but then likewise, changing that motion again and stopping the bicycle from moving is easier than changing the motion of the car and stopping the car from moving. Okay, moving on now to Newton's second law of motion. So what does Newton's second law of motion describe? We say Newton's second law of motion describes how the motion of an object changes when an unbalanced force actually acts on the object. And this law does have an equation associated with it. I'll ask this question here and then we'll go on to that. What is the acceleration of an object, or what states that the acceleration of an object depends on the mass of the object and the amount of force applied to the object? And the answer is Newton's second law of motion says that the acceleration of an object depends on the mass of the object and the amount of force applied to the object. And when you read that, I recognize that it seems kind of complicated. There's some big words in there and a little confusing, but this law is actually by far the most common sense law of all of the three laws of motion, and we'll get into how that is. But again, like I said a minute ago, there's an equation associated with this. There's one equation that we could manipulate in three ways. I talk about two of these ways in our class. So the first equation is that acceleration, A equals F over m. That is, acceleration is equal to the force divided by the mass of an object. Probably the most famous version of this equation, though, if we manipulate this equation to find force, we get what is probably the most famous version of this equation, which is force equals mass times acceleration. F equals ma. And I've already said this a few times, but the A is the symbol for acceleration, capital F is the symbol for force, and lowercase m is the symbol for mass. So force, mass, and acceleration are all related, and this is one of the things that Newton brilliantly came up with his second law of motion. And again, like the first law of motion, this law is better understood in two parts. So what does the first part of Newton's second law of motion deal with? Well, the first part of Newton's second law of motion deals with the fact that a change in the mass of an object affects the acceleration of the object. Okay, so I could ask the question, if force does not change and the mass of an object increases, what happens to the acceleration of the object? And the answer is, if force remains the same and the mass of the object increases, the acceleration of the object will decrease. And saying that and reading it might make you confused, but this is incredibly common sense. All this is saying is that if you take an object, and the picture over here on the right illustrates this clearly. If you take an object and you push it with some amount of force, and then you take the same object and you make it more massive, you add mass to the object. So in other words, it's more massive and it becomes heavier. If you then push that object again with the same amount of force as the first time you pushed it, it will accelerate more slowly. It will not speed up as quickly as the first time you pushed it when it had less mass. This is incredibly understandable. This is something that kindergartners, I think, understand just because they're alive in the world. You push a light object and a heavy object with the same amount of force, the light object will end up going faster. And that's what Newton's second law of motion says. Okay. Likewise, if you maintain the same amount of force on an object and the mass of the object decreases, what happens to the acceleration? Well, in this case, if you force remains the same and you push an object and then you make that object less massive, the acceleration will increase. So in other words, you push an object with a certain amount of force and then you do something to make the object lighter and you push the same object again, it will then accelerate more quickly. And again, this is common sense. A light object will accelerate faster than a heavy object if they are pushed with the same amount of force. Okay, what does the second part of Newton's second law of motion deal with? Well, the second part of Newton's second law of motion deals with the fact that changing forces applied to an object will affect the acceleration of the object. So here's the question, okay, if the force I apply to an object increases, what happens to the acceleration of the object? And the answer, the logical answer is, if the force of an object applied to an object increases, the acceleration of the object will also increase. So the everyday example of this is, if I have some object and I push it, and then I push the same object again with more force, well, when I push it with more force, it will accelerate faster, and that is common sense. And likewise, we could ask the question, if the force applied to an object decreases, what happens to the acceleration of that object? And again, logically, if the force applied to an object decreases, the acceleration of the object will also decrease. So this is saying, if I take the same object and I push it hard, and then I push that object again with less force, I don't push it as hard, it will not accelerate as fast as the first time I pushed it with more force. So the more force you push an object with, the faster it accelerates. The less force you push an object with, the slower it will accelerate. Common sense. Okay, Newton's third law of motion is the least obvious, I would say. And what does Newton's third law of motion describe? Well, Newton's third law of motion describes how all forces act in pairs. So what states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first object. And that is Newton's third law of motion that states this, that makes this statement. So, for example, when you jump, which direction do you push? And the answer is, you push down on the floor. So why do you go up? Well, the answer again is you go up because the floor pushes back on you with an equal and opposite amount of force. So when you jump, you're not pushing up, you're pushing down. But the reason you go up is because the floor pushes back up on you with the same amount of force that you push down on the floor. Now, this is not something that is obvious, I don't think, to most people, but this is the case with Newton's third law of motion. Okay, so what does Newton's third law of motion identify? Well, Newton's third law of motion identifies pairs of forces. So what are the two forces that Newton's third law of motion identifies? And the answer is Newton's third law of motion identifies an action force and a reaction force. So what is the force that is applied to an object? The force that is applied to an object, the initial force, the first force applied to an object, is the action force. So what is the force that an object applies back on the object that is applying an initial force to it? And this is what is called the reaction force. The reaction force is a force that essentially responds to the action force by exerting a force back onto the object that is applying an initial force to that object. So, when a force is exerted, what do you always get? You always get a reaction force and a single force, or can a single force ever act by itself? And the answer is no. And so what does Newton's third law say about all forces? And Newton's third law says that all forces act in pairs. So there are three questions there. What does Newton's third law say about all forces? It says that all forces act in pairs. And when a force is exerted, what do you always get? And you always get a reaction force. And the third question, can a single force ever act by itself? And the answer is no. A single force can never act by itself. And this is similar to the idea of forces in general. Forces always act on objects. And so what you have is you have a force is a push or a pull, and forces always act on objects. So what you always will have is you have a force, you have an object that is pushing or pulling some other object. So you always have two objects at least involved when you have forces, when you have a push or a pull. If there's nothing to push or pull, you can have no force. And if there's something pushing or pulling, it must be pushing or pulling something else. So you always have paired objects, and what Newton's third law says is you always have paired forces as well. And there's a paraphrase to Newton's third law that is pretty famous. What is the paraphrase of Newton's third law of motion? And the paraphrase is that for every action, there is an equal and opposite reaction. Every action has an equal and opposite reaction. And the pictures down here below show all sorts of examples of how motion comes about from Newton's third law of motion. When you're swimming, you're pushing backwards on the water, and the water is pushing forward on your hand, which is the example that's shown here with the swimmer. You have a rocket taken off. The thrusters inside the rocket exert a force on the gases, the exploding gases of the rocket, and those exploding gases exert a force back on the thruster that's powerful enough to lift the thruster and the rocket itself off the ground and propel it into orbit. When you're jumping again, you're pushing down on the ground pushes back on you to allow you to jump, and so on and so forth. Okay, the last topic in this unit is the idea of momentum. So there's a question here in the notes. It says, imagine a small car and a large truck traveling at the same velocity. Which one would be easier to stop? Well, you can assume from the question that the small car has less mass than the large truck. And it's kind of an obvious answer here, that you would think that the small car would be easier to stop than the large truck if they're going at the same velocity. And so that's our answer, probably the small car, and this is because of this thing called momentum. Okay? Now, what does the momentum of an object depend on? Well, the momentum of an object depends on the object's mass and the velocity of the object. So, what is a quantity defined as the product of the mass and the velocity of an object? And this is what momentum is. And momentum, what's the symbol for momentum? The symbol is lowercase p. And so momentum can be kind of a difficult idea to understand sometimes. For me, it can be sometimes. But really, it's a way to talk about, in a sense, how powerful is a moving object. Like how it's kind of like force. It's not exactly force, though, because it relates to velocity and not acceleration like force does. But it talks about really how hard is it to stop the object, or how hard is it to force an object that is moving to change its direction. So the momentum is all about moving objects and sort of how much force or power they have. So if an object has, the more momentum an object has, what happens to the force that it takes to stop the object? And the answer is the more momentum an object has, the more force it takes to stop the object. How about the more momentum an object has, how does this affect the amount of force needed to change the direction of this moving object? And the answer, likewise, is that the more momentum an object has, the more force it would take to change the direction of that moving object. So momentum deals with changing the direction of moving objects or stopping moving objects. How much force does it take to be able to do that? And most of the time in practical applications with momentum, we talk about collisions, moving objects colliding with each other. So there is an equation that we can use to calculate momentum. So what is the equation? Well, the equation is P equals m times v bar, which is momentum is equal to mass times velocity. P is momentum again, m is mass, and v bar is velocity. So what are the units of momentum? Momentum has the units kilogram meters per second. That's how you say it. Kilogram meters per second. That's how you say the units of momentum. And that comes from mass in kilograms being multiplied times velocity in meters per second. So like velocity, what does momentum have? Like velocity, momentum has direction. So momentum has a direction. So what can we say about the direction of momentum related to an object's velocity? Well, the direction of an object's momentum will always be the same direction as the object's velocity. So if an object has velocity, it will have some kind of momentum because it's going to have mass and velocity. Mass times velocity will give you momentum. And the momentum will be in the same direction as that object's velocity. So next question. If the mass of an object increases, what happens to its momentum? We can say if the mass of an object increases, its momentum will also increase. Next, if the velocity of an object increases, what happens to its momentum? We can say if the velocity of an object increases, its momentum will also again increase. So if the mass of an object goes up, its momentum goes up. And the opposite statement is true. If the mass of an object goes down, its momentum will go down. If the velocity of an object goes up, its momentum will go up. If the velocity of an object goes down, its momentum again will go down. Okay, now like I said a few minutes ago, most of the time momentum deals with collisions, the collision of objects. Now there's a law associated with momentum. So what happens when a moving object hits another object? Well, the answer is that some or all of the momentum of the first object will be transferred to the second object or to the object that is hit. What happens to any momentum that is actually not transferred to the second object that was collided with by the first object? Well, the answer is any momentum that is not transferred to the second object will stay with the first object. Can momentum ever disappear? The answer is no. Momentum in collisions can never disappear. Momentum is always conserved. And so this leads to this statement. What states that any time objects collide, the total amount of momentum stays the same? Well, this is the law of conservation of momentum, which says that any time objects collide, the total amount of momentum will stay the same. Okay. So this law is kind of like the law of conservation of energy, which says that energy cannot be created or destroyed, but it can change form. Momentum is kind of similar. Momentum cannot be disappear, but it can be transferred from one object to another. Now, is this law, when we observe collisions, does this law appear to be true? And the answer is no, the law does not appear to be true because there are other forces acting on the colliding objects. When is this law true? Well, this law is true if there are no other forces acting on colliding objects. The problem is that there's always friction involved, at least, when we have colliding objects, and friction is another type of force. So the law of conservation of momentum is the baseline, but then there's always some variability involved because of the other forces that are always involved when we have moving objects and colliding objects. Okay. When does the law of conservation of momentum apply? Or actually, a better question might be, what are the two situations that can occur when we have colliding objects? And the two situations are that we can have objects sticking together, or we can have objects that are bouncing off of each other. Okay, so first we will talk about the situation where objects collide and stick together. So sometimes objects will collide, or that collide will stick together, and we often see this in football, which is a good example of momentum. We look at momentum in football games all the time, where you have two colliding objects, especially objects sticking together. Usually in football, you have objects collide, and you have the defender tackling the ball carrier and holding on to them if they're making a good tackle and bringing them down eventually. Now, when objects collide, how do they move? And the answer is that after colliding objects stick together, when objects collide and stick together, they will move as one object. What direction do colliding objects move when they stick together? And the answer to this is that objects that stick together after a collision will move in the direction of the object that had a greater momentum before the collision. So when we're looking at two colliding objects that end up sticking together after they collide with each other, we can predict the direction that they will move after the collision if we know the momentum that each object had before they collided. The object that has more momentum before a collision, where the objects stick together, will force those two objects, when they collide and stick together, to move in that same direction. So there will surely be a change in the speed of the objects, but we can make a prediction about what direction objects will move based on their momentum before a collision. Okay, the other situation that can happen with colliding objects is that they just simply bounce off of each other. So other times that objects collide, they will just bounce off of each other. Now, when this occurs, what happens when in collisions between objects that bounce? So again, what happens in collisions between objects that bounce off of each other? What happens to momentum? And the answer is that momentum is usually transferred from one object to another that causes them to move in different directions at different speeds. Okay, next question. What happens to the total momentum in collisions in which objects bounce off of each other? Well, the answer is that the total momentum in these types of collisions will still remain the same, even if the objects bounce off of each other. So the example that's shown here is a good example. You have bowling. In bowling, you'll have the bowling ball moving down the lane, and as it goes down the lane, it has some mass and velocity, and therefore some momentum. Well, what happens when the bowling ball strikes the pins, those pins, which were originally sitting still, so therefore had no velocity and no momentum, all of a sudden some of the momentum of the bowling ball is transferred into those pins, and they go flying off in different directions at different speeds. And because they have mass as well, each of those little pins has their own momentum. And the bowling ball itself also will continue on, probably at a slower speed, probably change direction a little bit, but it will still continue moving. And if you took all the momentums of the bowling pins and the bowling ball together and added them up, they would equal the original momentum that the bowling ball had before it struck the pins. So all that momentum would be conserved in an ideal situation. Now, obviously, we're always going to have friction, which is going to affect that, but absent friction, you would have all the momentums before and after the collision would remain the same. Okay, Which of Newton's three laws can help to explain the conservation of momentum? And the answer is Newton's third law of motion can help to explain the conservation of momentum. So, good example is billiard balls. So if you're playing pool, the proper term for that game or that sport is billiards. So you strike the cue ball, which is the white ball when you're playing pool, and the cue ball then applies a force to one of the balls that it strikes. Well, what is that force called? That is the action force coming from the cue ball, and that action force is applied to the one of the billiard balls that are hit by the cue ball and causes that ball that's been hit to move. So there's a transfer of momentum and there's an application of force, and that is the action force that occurs. Now, that's not all that happens, though. There is the billiard ball that is hit by the cue ball will then transfer force, a reaction force, back onto the cue ball and potentially cause it to stop moving. If it doesn't cause it to stop moving, usually what will happen is it will cause it to slow down or change direction. And as a result, you have a shift in the momentum, but the total momentum, if you add it up between the cue ball and the billiard ball, should still remain the same. And this is also a demonstration of the action and reaction forces. The action force applied to the billiard ball by the cue ball causes the billiard ball to move, but then the reaction force applied back by the billiard ball to the cue ball will cause that cue ball to either stop moving or to change its speed and direction. Now, because of what Newton's third law says, the action and reaction forces are what? According to Newton's third laws, well, the third law, it says they are equal and they are opposite. And so what does that say about momentum? Well, that explains how momentum will not be lost or gained. There is no change in the total amount of momentum because the action and reaction forces are actually balance each other out. So this is the end of your notes. So you have your test tomorrow. Hopefully this is helpful for you.